continue from where we stopped. We are going to continue from where we stopped. We started with data models. We're able to understand the different types of data models that we have. And then we discussed the vector and the raster data models. These important data, environmental data, can be captured in different data model formats. So it's not just a single way of getting our data that maybe some persons have known about. We have the diverse models, and that is why we have different systems storing data in different formats. So as an environmental expert, you are supposed to understand these different formats anytime you are working on your research. So let's proceed to the third one, which is the TIN. And related irregular network model. So basically, the TIN model is a vector-based representation of processes, like the elevation or terrain data. So it is represented in 3 dimensions. It can give us a 3-dimensional surface, which can explain the slopes and elevation of a particular surface. So if you break down the area into irregular triangles formed by connecting nearby points, it is able to reveal the bulges and the depressions on the surface. And these are known as elevation or other continuous variables. So this model basically works by dividing the surface into different triangular shapes. They are formed by connecting the points together, which are called the nodes. So you have bigger triangles, smaller triangles, medium range triangles. Everything is connected, interconnected. And then you see a very fine 3D surface. So the nodes have X, Y, and Z coordinates. And each triangle is a facet in the TIN model. So it is used for terrain representation. So example, you can example, we have the watershed analysis, the slope and aspect determination. So I will show you the diagram so that you can see. This is what I'm talking about. This is what I'm trying to explain. You'll see that the shape that is here is gotten from these little triangular shapes that are joined together. They are jointed together by these nodes. Each point is joining another one. You have bigger, smaller triangles, that reveal the rise and fall of the terrain. So close to your eyes, this is what you see. And when you have a larger surface, or maybe you project it so that it shows a wider area, that's what you see. The same way with this one. So this is what you can get directly from ArcMap software. Run it in app. The result shows this. Of course, you can see these blue areas. These are showing us the depressions where you have the streams and the water lines. Then you have the elevated areas like the hilly ground. So you can see everything exposed. So this model, if you are doing your flood analysis or water catchment, watershed analysis, water catchment analysis, if you are doing urban planning to know areas that are susceptible to flood damage, this will be helpful. So this is what you can get. So a closer look at what is here, you will see how the edges are formed at different bearings, and the nodes are joined together. You can see the triangles, different shapes and different sizes. These are the points, you can see them here. So what you have here, you should be able to get this. So you can join up this one here, join to here, and then this one. This is joined to this one. This joined to this. And then from here, this one is joined to this to this, and then the whole area being covered. You will see that the 1550 is the highest peak, and then the 30 is the lowest. Let's see, yes, 45.2 is a lower point, but 35, I think 45 is higher than 30. You can see this is 45, this point here. So you can see from the software, the ArcMap or the ArcGIS. So the layers created from digital elevation model, we call it digital elevation model. So you can have the hill shading, the slope, the aspect, the curvature, the view shed, the water flow, and the watershed. So with this data can be downloaded from the NASA's archive. You can also get it from other data providers, like the shuttle rudder data service. I think SRTG them, they also have it. Then the NASA Earth data, you can also get it from there. Then there's another site, Jiva DIS, Diva GIS. I think Diva GIS. You just Google Diva GIS, and then it will take you to their spatial data. You will be able to get elevation data. The data looks like this. When you input it in the software and allow it to run the slope, this is what it is going to give you. When you run the TIN, it will give you something like this, which is the aspects. When you ask this same software to use this same data to produce the hill shade, it is going to shade it and give you something like this. So it depends on what you want to to achieve in your model. So this is just the raster. This is a raster model which can be converted to this form. So you can see the points. These are the facets. So you can run it. This is the grids. You can move from this to this or this to this, depending on what you want. So uses of TIN. TIN can be used for terrain representation. It can also be used for hydrological modeling. You model for watershed, you delineate stream networks, and also model water flow across the terrain. It will show you the direction of flow to see how the terrain is affected from multiple water flow across different seasons. You also have slope and aspect analysis. Teams are also effective for calculating slopes. You can show the steepness of the terrain, and for aspects, it is able to show the direction that the slope faces. The same thing I was trying to explain. If you run this analysis, it will show you the direction of the slopy ground, whether it's sloping the other way around or whether it's sloping the opposite way. And these analyses are essential for understanding the erosion potential, vegetation growth, solar radiation, and other environmental factors. There are some projects that one may need to site on slopy grounds. So carrying out this analysis will show you how you can better site your projects. For example, a windmill. If you are looking for areas to site your windmills, you can run this. It can show you uh, higher grounds, because we are not supposed to site our mills in areas that may disrupt, maybe, or may be very difficult for movement of the equipment. So the windmills are sited on high altitude, high terrain, where the ground level is so flat for easy movement of the equipment. That is when you are dealing with the giant wind turbines. So the TIN can also be used for 3D visualization. They are widely used for surface visualization in 3 dimensions and are widely applied in urban planning, geological modeling, and virtual reality. So this is able to create very fine images that can be so appealing, and they reveal details about the terrain. Contour mapping. The TINs are also used to generate contour lines, the lines of constant elevation, which is useful in cartography, civil engineering, and environmental analysis to provide elevation data maps. You can also use them for volume calculation. They're used to calculate volumes of features such as cut and fill operations, where you need to do maybe some gigantic projects during the EIA process. They use methods like this to find or to calculate volumes of features, maybe in or aiming at maybe cut and fill operations during construction, excavation projects. We can also use it for site planning and development. The teams are used for site planning, road design, and construction projects. So environmental impact assessments, I mentioned that, used to model landscape, understand how certain actions like building dam or road might affect the environment. We also use They're also used in geological modeling. We also use them uh, for slope stability and landslide analysis. You can carry out landslide analysis with the help of the TIM model. So by analyzing the slope of terrains, environmental scientists and geologists can be able to predict areas that are prone to landslides and also propose preventive measures. We can also apply it in urban development. So let's look at the network data model. Each one has its own unique way that it can represent or it can represent variables. So let's look at the network data model. We talked about vector, raster, TIN, and let's look at the network data model. The network data model is used to present interconnected linear features and is applied primarily in transportation and utility networks because we also have features which appear in form of lines. We need a data model to be able to represent such features. We have features like roads, we have features like streams, we have so many features that can take this shape. So this can be modeled in form of a network that once you run it, it is able to give you a particular result or representation. And remember, I told us that this is just an abstraction of the real world. So in smart cities, we have these models, the network models that are used for simulation of even the street construction. You don't just construct streets in such cities because if you put up a street anyhow, it is going to obstruct flow during high traffic conditions. So before you do that, you simulate and know the length, the location, and maybe the space the road is going to take. It gives you the results. You do this before you go ahead with maybe development of a project. So a network is an interconnected set of points and lines that represent possible routes from one location to another. So a flow network is characterized by its topology and flow characteristics, such as capacity constraints, path choice. You are going to get maybe a choice location, how you want the, the road to follow, and how you may want the road to link with other existing roads. So we have the path choice and the link cost functions. This is based on Fisher 2004. So if you Google Fisher 2004, you are going to get it. He worked on this network model. So it is done so that it will be easy for evacuation during emergency conditions. We don't just talk about this. In our country, we ignore these, uh, most of these models in our development. That is why at times when there's an issue, when there's an emergency condition for maybe a fire service truck to move from one area to another, at times you see that there'll be a lot of issues on the way. So, but with these models, they know they can compute the time taken for the truck, or from the model, it will show you the nearest fire service uh, center that can serve the particular region. So uh, we have a lot of applications of this network data model. So the elements of a network are the nodes and links. So in the other times we are asked this, I think one is assessment. What are the elements of a network data model? So you just have the nodes and the links. The links are just the roads or the directions themselves. The nodes are where the roads are are intersecting and linking up with other existing roads. So the nodes represent points of change and intersections within a network. Links are linear features made up of two or more nodes. So from and to, that is, it's supposed to be fro and to, not from. Fro and to. So I'm going to correct that. That represent features such as road, rivers, and railroads. The attributes of nodes and links are stored in tables and assigned unique identification numbers, which are referred to as key fields, known as relational database. Everything is stored in a database. So that is why the smart cities, if you visit the Beijing and you have chance to travel by their bullet train, the bullet train runs at 380 kilometers per hour. And there are some nodes where the train, you have like 10 trains intersecting, something like this. You have 10 trains that are supposed to pass at sea in less than 10 minutes. So maybe you have like two coming this way, three coming this way, you have two this way, three this way. And maybe this one comes like this, goes like this one comes, uses F to G, this one from B to H, and then this one A, C, F, G, like that. So they have a very complex uh, network system of the array. So just imagine the array system where the trains are moving at that kind of speed. So there is no excuse for error occurrence. So they try to maintain a very high level of accuracy. So that is why you see trains, if you see one train is programmed to pass, maybe after like 10 seconds, another one will pass. 10 seconds, they can control that on their model. So that is why they develop these models for their own application. So when we are talking about these models in our own case, where we don't experience this kind of complex topography, if you look at our roads, We don't even have complex roads. Let me say in our states, it's nowadays that they're trying to kind of open up roads. When you have a lot of links and nodes, you hardly see a lot of cars on one road. Before, if I'm moving from maybe from Air Force Base to Wurukum, you have a lot of cars moving that way and then the opposite direction because you hardly get other shortcuts to get to your destinations. Same way when you are coming from town, maybe Wurukum to Uniagric, you don't have any other way except people coming from North Bank, people coming from town that will meet at SRS. Everybody is following that uh, single lane to school. So you have a lot of congestion and very difficult to model. You might not understand maybe the beauty of this. So, but in countries with organized transport systems, they make use of these models. So you have physical network graph, something like this. So these are the nodes. Then these ones, the numbers are the links. So you can code this in your database. And you can see that the ID is labeled as A, B, C, which are the nodes. Then the location of the nodes is given by X and Y, which are the eastings and the northings. You could also call them, or you can use the latitudes and the longitudes. And then the connectivity. You can have A, the connectivity is 1. Uh, Connectivity is 1. And then B is 1. Let's see C, how many? 4, because it's connected 1, 2, it's connected to A, F, D, and B. Like that. G, you have 2. This is D and F. So the same thing. You have the ID for this. 1, you have from A to C. You have A to C. The G score is 68. I think this is for modeling sake. This is for a network that has been already programmed in the model. So you have a score depending on the kind of model you want to apply for the score. So it could be length, maybe the length. So this is the GIS network, network model type. So a GIS network can be constructed from various sources, such as the river network. So if I ask you to write a short note about the network data model, I think you should be able to write at least 2 lines. So it can be constructed from various sources, such as rivers. I told you, you can use rivers, you can use the roads, the train, the rail systems. If you are opportune to work with OpenStreetMap, it's you can just Google OpenStreet. You are going to see the map of the towns. If you just Google Makurdi OpenStreetMap, Google Makurdi is going to show you Makurdi with the roads and the buildings. You'll be able to see the roads, the water bodies, that is the streams, the rivers, the rail network. You see the railway line from, I think, the Eastern Railway from Port Harcourt to through Benue to through Kaduna. You should be able to see the rail track. And then, oh, sorry, through Jaws. I think our own passed through Jaws. It's the one that passed through Jaws. So, use cases for modeling and analyzing road network. That is the shortest path. The route, you can use it for route optimization to know the shortest path. I mentioned that earlier. In case of emergency situation, you can compute and know the shortest path for an emergency vehicle to take. You also have utility networks in big towns, big cities. You have this network for water, network for electricity, pipelines, etc. They have a wastewater network, so they don't allow individual homes to maybe construct the sewer tanks and be disposing. Everything is connected in form of a network and linked to a central processing uh, unit. So for this town, we can have a central waste processing unit, and they rather make money from the waste management because they have the network that pulls or sorts waste from individual houses, transports to the waste management system, they recycle. I think at first they suck it, recycle it, remove water, and channel the water back to your your sewer system. So that is why it is advised that you don't just drink water anyhow. When you see water leakage by the roadside, you don't just drink. In most countries, they they, they place restrictions because you might be drinking a recycled water from the waste management network system. So they recycle that, and then so at times maybe what you are taking your bath with is what has been recycled and pulled up into your head tank for reuse. Or maybe a main recycle is separated just for uh, the lavatories, that is for toilets, and then the other one from the public treatment plants is the one that you use for taking your baths. So anyhow, it depends on the kind of arrangement in that country. So these are various ways you have your data because these are models that are used for environmental research. So you have the utility networks, which are water, electricity, waste management, is the pipelines. For the oil industry, you can also have their own network. I think in China, because I'm very conversant with Chinese system, you hardly see any truck moving fuel from one, I think, one town to another. It's very hard, you see, because everything is connected on the ground. If you are building a new fuel service station or a filling station, all you need to do is just to pay money, and they will just trunk some pipes and connect to your station and put a metering system for you so that what they're giving to you will be read by the system, and it's digital. It's not something they do by manual. So but in our country, I don't know why we try to maybe uh, evade these complex systems. I was told that previously, the AP depot that we have in Makurdi, AP depot used to receive crude oil fuel from Port Harcourt. To pump from Port Harcourt to Enugu station, the Enugu station will pump straight to AP. So from AP depot, at least it will save the stress of traveling with your truck from Makurdi to Port Harcourt to the refinery to go and buy the fuel to come and distribute to the filling stations. So they used to just drive down to a P depot, load their trucks, and then service the towns or the northern states. So, but with time, when we said I was opportune to visit the refinery, and we're told that why they stopped pumping was that if they pump, the metering system at the refinery will show maybe 1 million liters pumped. When you ask a P depot will tell you that received only 500,000. And then, so the computers will be reading. So in between, you have some quantity lost. So they couldn't continue with the shortages. That was why they had to short most of this. They had the refinery at Kaduna. They used to pump straight to Kaduna, so that it can serve the northwestern states. So every arrangement was in place. But over time, we had some saboteurs. So you can work with this system. I think with all this on ground, all we needed was just to improve from this network. Our target should have been maybe to improve the network, to maybe have another depot around Adamawa, or maybe another depot in Sokoto, and then in future try to have like maybe pairing like two states to one depot, creating that network to reduce the movement of heavy trucks. And one thing we don't know, because we don't look at these researches. So why we mention this is, by the time you are looking at these models, you should be knowing why. Some persons, our roads don't um, uh, stand the test of time. Like, you construct roads at exorbitant rates, and you discover that they don't take up to 15 or 20 years. You discover that almost every, let me say, 10 minutes, you have trucks moving petroleum products to and fro. How are the roads going to survive? So that is why developed nations, they have their own way of solving these issues. Because if you run away from one, you are going to still incur the loss or the losses the other way around. So you don't want to develop your distribution network. You keep fixing your roads. You keep fixing your roads. So, but if we come about a very, I think somebody can do research on that, how to, you can use the existing petroleum supply network, do a model, how it can be metered using digital technology, so that fuel pumps from the main refinery, or you can even do this for Dangote, suggest for him. You know, he has a refinery in Lagos at the free trade zone, can do a network model for him for his distribution points or nodes. Those should be nodes, and then you have links. This will serve here, this will serve here, so that maybe in less than 6 hours, the trucks shouldn't be moving longer distances. I think these are the models we should be doing, even if it's not going to implement this? I think one can think about such a model for environmental sustainability. It is eco-friendly. It reduces the amount of carbon emissions, because a truck traveling from Lagos to Sokoto or Lagos to Benue State, you can compute the amount of the petroleum products or the petroleum emissions. If we look at the carbon footprint angle, how much is being emitted daily. Then recently we have about 2,000 or so trucks that even plan to import more, maybe making a total of 4,000. So just imagine all the trucks giving out emissions, maybe 0.05 grams per second on the roads. That is a whole lot of pollution. So, but when you distribute using these networks, maybe a trunking system, this refinery can be linked to some minor, stations called the nodes, and then the system is protected. I think it will be very, very sustainable. So this is one way we can study this. So you have rules, you have any variable that you can model that will take the shape of a road. You can apply the road network. The shape of a line. Sorry. So I've uh, I've placed these shots for us to see. This is the digital elevation model. This is a raster. I told you you can have like one or two models appearing in another model. So you have the DEM. The DEM is a raster. Look at the grids. Look at the picture very well. You see the grids. The smaller grids is just that the picture is a little bit small. So this is shaded. This one is shaded, but it's still a raster. And then it is from this that we have created the river network. You can see this network here. You can see the river channels from digital elevation model. You can see the channels here. You can see the river channels. So you can use the raster to create a river network, and the river network can be used to work the network model. So the same thing here, you have the aerial photo. Now you have the roads. Look at the roads. I've drawn them in red so that you see. These are the major roads. Maybe you can use our town. You just use maybe the primary and the secondary roads. We have different types of roads. We have the primary, the secondary, we have the trunk A roads. We have the federal and the state roads. And then even the tarred roads are of different classes. You have the tarred roads, and then on tarred roads, you have the footpath. So even if you want to study about the road network in our state, it's still going to give you a good representation. So from here, you can just pick the main roads and then get your network. So from here, you can see have the links and the nodes. These are the links. The black ones are the nodes. So this can be done in the software. The software can do this for us. It's just for you to know the commands. So let's look at the accessibility measures based on the network digital model. The shortest path, we call it the network distance. For example, if you want to move from start point to the end point, you seek to follow the shortest. Okay, you might choose to follow here, you might choose to follow this way. I'm just giving you an example. So we have a definition for the shortest path because we have an analysis for this. So the SP analysis is a fundamental application in network analysis, which is known as the network distance. So the Dijkstra is the common algorithm used in finding the shortest path, which is also which also has a lower computational complexity, according to Zhang and Noon, 1998. So the Dijkstra's algorithm computes the shortest path from a selected start node to any node you can think of, any connected node. So you can use it to compute. So it is going to show you whether this is the shortest or the longest path. Then we also have the directness measure, which is the measurement of the network efficiency and complexity by rationing straight line distance, which is referred to as AD. So the straight line distance and the network distance. You have SD and ND. So the value is between 1 and 0, where the most efficient and simple network has a value of 0. So when you see values closer to 1, you know that the road network is very complex. So the models are already there. So before construction, they already know if their target is to link a particular town with another one, or link any emergency facility with the town. They know how to place the routes, compute this directness, shortest path, network distance. And so they compare the values for different directions to know what they want. So the alpha index. The alpha index is a measurement of the connectivity level. So if the alpha index is high, you note or you notice that the road will have high connectivity. So if the alpha index is maybe closer to 0, it means the road has less connectivity. That is links across the different nodes. So a value of 1 indicates a completely connected network. So it is very rare that an actual network will have an alpha value of 1. So it is very, very rare, except for some smart cities. We have some cities in Japan that are so neat because they were planned from scratch. The road network systems and everything were planned. So you could get values closer to 1. But in our own situation here, that we can wake up and just decide to point your finger that this is where you want the street to pass through. Another person will come and build his house closer to the street, and maybe in trying to construct the street to this size, it is going to affect maybe the length or maybe the straightness of the streets, causing maybe a diversion, or at least a lot of issues come into play. So the formula for alpha index is equal to links. You have the links minus nodes plus 1 divided by bracket open 2 times nodes minus 5 bracket close. So this is the formula. So for example, if you have 8 nodes, 8 links, so you are going to put 8 minus 8 plus 1 divided by 2 times 8 minus 5. So the answer should be equal to 0.09. If you do for this one, the answer is the same as 0. So I always show you, I ask them to write short notes about alpha index and gamma index. I gave them something compute, not exactly this. So go and look at this. So the index is a ratio of the number of links in the network. Why the alpha index shows the level of connectivity. The gamma is the ratio of the number of links in the network to the maximum possible number of links between the nodes. So the maximum possible number of links is expressed as minus 2. So this is the formula. Look at the formula here. This is the formula. You have links divided by 3 bracket open nodes minus 2. So you can use the same method, compute for this and this. So you see. So you see that this one has less connectivity because the links are higher by 1 for B, which is 9. Yeah, you have 8 here. So you notice that the gamma index is 0.4 when the links are less. And then you see that one additional link here makes the gamma index 0.5. So the more complex the road network, you see that it shows you a different value. And this one too is telling you that as the connectivity increases, you see that the value approach, the value tries to maybe get closer to 1. You notice something closer to 1. Connectivity mean center. So the connectivity mean center averages the x and y coordinates of all the nodes in a specific user-defined area, such as a planning zone or an administrative unit. So you look at this for this area, this is the connectivity mean center according to Luin and Murayama 2009. They were able to find the most connected place within a specific unit based on the number of connected streets. So based on their method, this area was the most connected street. So using the weighing factor, this is the method. You use x and y coordinates of the nodes. So each of the nodes have coordinates. So if you sum the W is the number of the connected streets in the node, X and Y are equal to the node I coordinates. That is node 1, node 2. Then X bar, Y bar are the mean center connectivity. So what you're going to do is multiply the number of connected streets in each node I. For 1, this is node 1. How many connected is 1? You are going to multiply by the x coordinate. So you have W times X for node 1 plus W times X for node 2 plus W times X for node like that. When you are done, W times Y for node 1, W times Y for node 2, like that. So you now take this over summation of the number of connected streets in the node. That is the links. Looking at the links. So you do this for X bar and Y bar. So it is going to give you the connectivity mean center. Given uh, for this image, it's found in this corner. So let's look at the shortest versus the greenest path. Sometimes road attribute values can be used as weighted factors to compare the shortest versus the weighted distance. So for example, finding the greenest route can be accomplished based on the greenest call of each road segment. These attribute values could also be speed limitation, the number of traffic accidents, the traffic volume. So you could have the greenest path and then you could have the shortest path. So from start to the end of this road, this is the greenest path, the path with the greenest vegetation, but you could have the shortest path. Maybe this straight path has a lot of emissions, so it's not green per se. You can also have the greenest path. At times, the greenest path is also the shortest path, but it doesn't mean that it must be like that. So you have the shortest path, you could also have the greenest path. So for this comparison, you just want you to know that you can have the shortest and the greenest paths at different locations, or maybe the distance is varied. So what they use is to weigh. They have weighted factors. So when you know this, it is going to be weighted, and then the one for example, the shortest path, summation D. They have like one plus, that is node 1 plus 3 plus, which is equal to 5. Then the shortest path, the shortest path 1 plus 3 plus 1 equal to 4. You also have 1 plus 2 plus 1 equal to 4. So you have this. So when you're looking at the greenest path, you have 4 plus 8 plus 4, which is 16, and then 4 plus 4 plus 4, which is 12. So they are entirely giving you different thing. So you also consider case 2. So at times we look at this based on the models that are going to be useful, though we hardly have most of these arrangements in our country, because if we're talking of this, somebody may ask me about the greenest part. If you know roads that are, yes, you have roads, but such roads, they have a lot of tree plantations, maybe on the road divider or by the sides of the road, so that the entire road has a lot of green vegetation, both at the divider, the road divider, and by the sides of the road. Such roads, we have some smart towns that they have taken time to develop their roads. But in our situation, not all roads that you can find this kind of arrangement. So you could look for the shortest path, and then you could look for the greenest path, especially when you have heavy solar rays. You are going to be looking for the greenest path so that you can take your shade. At times when I'm trekking, I also look for the greenest path. When you are trekking from south to north core, you will see that the road through the quarters has a lot of green vegetation, almost covered. Then when you take to the junction going to the gate, then from that junction to the solar farm, you hardly come across green parts because you have no trees beside the roads. So let's look at average block size and block density. Average block size, like this Hess et al. 1999 and Rayleigh 2002 can be measured by converting the road lines features to polygons and calculating the average block area. And then the formula is given by the average block size, which is equal to the total areas of the polygons and the number of polygons. Frank et al. Used the mean number of census blocks per square mile. Since census blocks are typically defined as the smallest fully enclosed polygon bound by features such as roads or streams on the site. Because a rule of thumb is that the smaller the size, the better the accessibility. So in this arrangement, you are just trying to get the average block size, and then you convert the road line features to polygon features, and then you calculate the average block area. So when you look at this is just an image showing different plots. So if you are able to convert the road line to polygon features, it will help you to calculate the average block area where the blocks can fully fit. It will just give you an estimation. That is why they are talking about the census blocks. That is the blocks that may even fill the areas that are supposed to be covered by the actual buildings in the compound. So let's look at the cumulative opportunity measure. This is what we're discussing is under the network model. These are the measures under the network models because they have different applications and complexity. So we have different measures. You have the cumulative opportunity, which provides a measure of the number of available facilities within a certain distance or travel time. Example of cumulative opportunity measures are found in various articles, these articles. So you can just draw this circle and then measure the number of supermarkets. You can decide to measure the number of communication masts, cumulative opportunity, the available facilities of interest. This is known as query. You can just query with a circle on your image. How many schools do you have in this space? Something like that. So A is given as summation B times A, small letter A. A is the accessibility measure, which is measured at point I to potential activities in J, all the activities of interest. A is opportunities in zone G, sorry, zone J. Then B of J is a binary or a threshold value. So you just apply this depending on the opportunity. This is just a very small formula. It has a modified version of it, depending on, you might decide to work with different. This area is a mining area, and your interest is on the different minerals in this zone. You can also create this to know the accessibility. So gravity-based measure is given by this formula. When you get this, you go through it. So the gravity measure is an interaction of nodes based on their distance and some functional weighted factors, and measure of their individual accessibility. So for example, weighted factors will be number of shops per point, frequency of going to these shops. The gravity model is sometimes considered as potentials model. So the higher the opportunity and the shorter the distance, the greater the interaction occurring between 2 points. That is like the Newton's gravity law. So if you have a shop, maybe a shopping mall around the solar farm, you will notice that if you have two, if you have one around the solar farm, then have one in North Core, then you will notice that students that are closer to North Core may not necessarily travel down to South Core because of the shortest path. They will try to make use of the shopping mall in North Core. Likewise, the same uh, arrangement down here. Students in South Core can shop at the shopping mall around the solar farm instead of going all the way to North Core. So the opportunity that presents in this case is you are having, because now you need your money to take you from here to North Core. Why should you spend money to go to North Core when you have the same opportunity around the solar farm? So maybe it's 100 naira is taking you to solar farm and 200 to North Core. You think that it's better for you to save that one. So the higher the opportunity and the shorter distance, which is why the interaction is occurring between the 2 points. That is why they are saying gravity-based measure. It's as a result of that, the shortest path or the shortest distance that is getting you attracted to a particular thing. I know that it is always difficult for engineering students to stay in South Core because of their lecture venues. If I stay in South Core, going to North Core every day is always stressful. The same thing with students that are taking science courses. If you are staying in North Core, then coming down here will prove difficult for you. So we're looking at the attraction. What is attracting you? What is attracting the movement between one object to another point? So we're talking about the Newton's gravity law. So Hansen in 1959 is generally credited with first applying the gravity approach to transportation and land use planning. So you can apply these methods in land use planning. So the next one is the geodata base. But before I move on, or maybe we may choose to pause here for now. I would like to take questions. I will take questions from the class before we know whether we'll proceed or we'll call it a day. So questions. Hello? Hello?
Sir? Hello.
Yes, yes, yes. I'm waiting for you people.
I said that when you were talking about those networks, I think those places you read, there are depots there. I think we have about 16 depots. Adama and
What?
we have depots in those areas that we were talking. That I thinking they need to. There's a network of depots. I think we have like 19 already. I'll be 18. There's network in
Okay,
Adama.
okay. Petroleum depot, right?
They have them spread around the country. I think the issue then was because of the vaccinations of, and I think Dangote will now. That's why Dangote is preferring to truck and in this CNG for the
Yeah,
environmental, because when we're still in the pipeline, those companies that those they didn't analyze hooks to them. Even the areas have, and the other thing was our refineries were not working. So that is why I think so
yeah.
that
Thank you for.
for gas, because people will not vandalize gas. You can see that they are doing new gas truck for petrol. I don't think Dangote. That is why Dangote is model. Thank you, sir.
Yeah, thank you for the contribution. It was a wonderful contribution. That is the essence of the class. You can contribute. If you don't have question, you can contribute so that others will also benefit. So, do we have any other person?
Okay, so it seems like they don't have any other questions to ask. So
It's okay.
thank you, sir.
So, yeah, so should we proceed or we call it a day for now? The class was originally scheduled between 1 and 2, and now it's 16. So I don't want to take you away from your time.
Oh,
Should we
yes, sir.
call
If
it
it's
a day
okay, I
and
think we can.
come back tomorrow?
Yes, sir. Yes, sir. Please, sir. Some
It's
already
okay.
indicating they have some engagement.
Sir?
Some students are already indicating that they have some engagement scheduled already.
They have some engagement. Okay, that is why I want to find out from you so that I won't. All right, so it's been a nice time with you. I I believe you will catch up with the class. Uh, and little by little, we understand ourselves.
Thank,
So have a wonderful day.
thank you very much, sir. You too, sir.
Yeah, bye.